In this video, we'll talk about time complexity. See, the thing is, in the previous video, we have talked about algorithms, right? Now, the thing is, if you want to build an application, basically we are trying to solve a problem, right? And every problem will have multiple solutions. So the steps which we write to solve that problem, that's what we call algorithm. Example, let's say if you want to cook something, you follow some steps, right? Now those steps are your algorithm. Example, if I want to record a video, we do multiple things. We prepare the content, we set up this camera, mic, and then we start recording, then we edit the video. So there are multiple things involved. In the same way, if you want to solve any problem, we have to follow some steps, which we call algorithms. And the thing is, for one particular problem, we don't have one solution. We have multiple solutions. And we have to pick the best one. Now question arises, how will you choose the best one? So when you say best one, what exactly it means? So let's say when I run this application, I want my application to use less memory. Or maybe when I run this application, I want it should take less time. Or maybe both. And that's why we have this term called algorithm analysis. So basically you have to analyze your algorithm so that you can make it more efficient. Right? Of course, as a developer, first focus is the product should work, and then you think about optimizing it. But when you say optimizing, you can optimize in two ways. One, think about the space complexity, and second is the time complexity. Space complexity simply means, can we use an algorithm which will take less memory? And time complexity means it should take less time. But there is one more problem here. And the problem is, how will you calculate the time, or how do you specify the exact time? Because every machine will have a different output, right? So if you are testing the algorithm in your machine, it might give you different time. And then the moment you test this in your office machine, it will give you a different time. So that's not the best thing to calculate the number of seconds it takes. But what you can do is, there is a way you can calculate with the help of steps. But before we go there, let's focus on two algorithms here, and then this will make much more sense. So the algorithm which we're talking about now is the searching an element in a sorted array. So in the previous video, we have talked about array, and then we have also talked about the sorted array. So in sorted array, by default, all the elements will be sorted, right? Now what I will do is, I want to search a particular element from this array. Now there are multiple ways of doing it. Let's talk about the two. So basically we have an option of linear search, binary search, or many more, but let's focus on this two. So what exactly linear search and binary search is, let's talk about that. So what is linear search? So let's say you have an array with you. Okay, so this is your array, and in this you have multiple values. So let's say I'm going with few values here. Let's say 5 values. And then I'm going to write, let's say 5, 7, 9, 12, 17. So we got this 5 values here, right? And then I want to search a particular element. Now this is sorted array because you can see all the elements are sorted. We got 5, 7, 9, 12, 17. And I want to search a particular element. Let's say I want to search 12. Okay, I want to search this element. So maybe there is a target value which I want to search. In this case, the target value is 12. So I want to search 12, right? And then this is an array. So what we do in the linear search is you go one by one. So what you do is, in fact, we have talked about this in the previous video as well. So we'll make it a bit faster. So what you do is, whatever your target value is, you will compare that with the first element. If it is matching, great. Otherwise, you will move to the next element. Otherwise, you will move to the next element. Otherwise, you will move to the next element. And I mean, of course, at this point, we don't have to go to the next element. So here, we basically got the value. And once you got the value, you can return the value, right? Now there's a problem here. The problem is, what if the element is not there in the array? So of course you have to reach till the end, okay? What could be the best scenario here? So let's say you are searching for an element. Let's say element is 5, and now we know element 5 at the start itself. So when you have the element at the start, it will take only one step. But what if you have element at the end? So it will take the steps depend upon the length of the array. So let's say if you have 5 values, it will take 5 steps. When you have 10 values, it will take 10 steps. When you have 1 million values, okay, that's huge. Let's talk about 1,000. So let's say when you have 1,000 values, it will take 1,000 steps. That's tricky. Right? Now the problem is not it is taking 1,000 steps. The problem is, as your size increases, it is also increasing the number of steps to search. Okay, that's one parameter you have to remember. So that's the theory, right? Now let's understand that with the help of a pseudocode here. So you can see I'm writing a pseudocode. Why pseudocode? Why not some programming language syntax here? Is because we wanted to make it generic so that you can, doesn't matter in which language you work, maybe C, C++, Java, JavaScript, Python, maybe COBOL, your choice. this pseudocode remains same, right? Now this can be function, procedure, doesn't matter. So what I'm doing here is we have a procedure, right? It can be a function, and the name of the function here is the linear search. Okay. Now we are accepting a list of items. Now this is your array. The name of the array is A. Okay. And then you are also passing a target, what you're searching. So in this case, we were searching for 12, but doesn't matter. So you have an array with multiple values. It can be 1 value, 10 values, 1000 values, doesn't matter. And then you're also passing a target, what you want to search. Now you will go inside this, and then for the first thing you will do is you will want to find the length of the array, because of course you should know, right, till when you have to search. So you got a length which is stored in the n, and then we are going from 0 to n minus 1, because when you start with 0 you have to end with 1 less, right? So if you have 10 values, you will go till 0 to 9. So you will go from the first value to the last value, and then you will search if the target which you are searching is equal to the current element where you are searching. So when you're searching for the first element, that's the first element here, target is matching. If yes, you're good. You can simply return the value. But what if you're not matched? It's not matching. It will go for the next iteration, next value. Is it matching? Yes, good, return. What if it's not matching? Next value. So basically you have to search each value till you're not finding it. So that's basically a pseudocode here. And what if there's no element? Example, you have 5 values and you're searching for a value which is not there. You can return -1 by specifying, hey, the value is not there. This is simple linear search. The code is small, but then the time complexity, which is the amount of time it takes, is huge. Okay. Now let's go for the second approach, which is your binary search. Now what happens in binary search is it's very simple. Basically, it's not that simple, but let's say. So what you do is you have an array, again, a sorted array. And let's say we have multiple values here. I'm not sure how many lines I'm going to draw. So let's count it later. So let's say we got 5 here, again 6, 8, 9, 11, 13, 17. Okay, so maybe I love odd numbers. So it doesn't matter what values you have there. So we got 1, 2, 3, 4, 5, 6, 7. So we got 7 values, right? Now what you do is in binary search, now since this is sorted, if you're searching for a particular element, let's say I'm searching for 8 here, okay? And we know 8 is here, we know it, but computer has no idea where 8 is. So how it is going to search? Now in linear search, what we were doing is we were jumping basically from value to value, searching, checking this, and then goes on. So now why this called binary is because you divide your array into 2 parts. That's the binary is. Now how you do it? So basically what you do is you give a starting point and then you give a ending point. And of course, every element here will have an index value. So in total here we got 7 values, right? Which goes from 0 to 6. Now what you do is you first divide your array into 2 parts. And to do that, we have to find a mid value. Okay, so even before you divide, you find a mid value. So how do you find a mid value? So mid value is equal to the starting position plus ending position divided by 2. Okay, now this is 6 divided by 2, which is 3. Okay, so your mid now is 3, and this is your mid. Okay, now basically you check with the mid. Okay, so you always check with the mid. Is the value which you are searching for, which is here, is it matching with the mid value, which is 9? No, it's not matching. But is it less than or greater than? If the value which you're searching for is less than the value which you got as a mid value, then the values after the mid value is of no importance, right? So this values here has no importance. You can directly skip them. So you can divide your array into 2 parts. So you got the first section here, which is 5, 6, 8, 9. And then you got the second section here, which is 11, 13, 17. So what you can do is you can basically skip this part, or maybe I will just do that with a color. Now we can skip this part. We don't need this value. The value which you want to focus on is 5, 6, 8, 9. So what you do now is you make your mid as the end, okay? Because we have shifted to the left part of the array. Now of course, when you shift to the right part of the array, in case, then you shift your starting value. Now here you got S and E again. And then what you do is you again check your ending, you will find your new mid value. So again, S plus E divided by 2. Now S is 0, 0 plus 3 is 3 by 2, which is 1. Of course, you can say 1.5, but let's say this is 1 equal to 1. We can apply a float function to get the nearest integer. Okay, so we got 1 here, right? So what you do is you check. So this is your mid. Again, you check, is it matching with the value? No, it's not matching. So 8 is not matching with 6. Then what you do? Then you again divide your array into two parts. But then which one you have to skip now? Now we know that the mid is 6. So we have to jump to the next value. I mean, we have to look at the right side value. So 6 is less than 8, right? So we have to look at the right side. So now what we're going to do is, we have divided into two parts, right? So now we can skip this part and focus on the right side now. So your starting position has been moved here now. Now this is your S and you got E. So again, you will find a new mid, which is S plus E divided by 2, which is 1 plus 3 is 4. 4 divided by 2 is equal to 2. So your mid now is 8. Now is it matching? Yes. Okay. And that's how you got the value. Now, if you might be thinking we have done so many steps, right? Not exactly. Basically, at the start itself, we have removed half of the array, and which is very important, right? So let's say if you have an array size of 1000, at the start of the first operation, you have removed 500 values. For the next operation, when you do it, you remove 250 values. So the number of operations which you are doing with binary search is less, right? And that's how you know that this is better than the linear search. Of course, in linear search, if the value which you're searching for is the first value, it's very fast, right? It will take a lot of time for binary search. But in general, binary search works faster. But how do you do that? So with this theory, let's talk about the practical implementation here. So let's look at the code here very fast because we have already done the theory here. So what you do is you basically write a function, let's say binary search, and then you pass a list of values, right? And then you also pass a target, same thing we have done in the linear search. And here, then you go with the left and right. So basically we have mentioned the start and the end. Here in this, we are taking left and right. Left starts with 0, as we mentioned, the starting starts with 0. Ending ends at the last value. Okay, we have done that. And then you run a loop till you find the value, of course. Then what you do is you check the mid value. So this is the mid value. We have done that. Mid is the starting point, ending point divided by 2. And then you check, is the mid matching with the target? If yes, you're done. You can simply return the value. Otherwise, we have to do something more. Then you check if the value which you got, which is a mid value, and the target, if the mid value is less than the target, in this case, you will focus on the right hand side. Okay. So basically you have to shift to the right hand side. So your left, your starting point will shift. And we have discussed that here, right? Your starting point will shift. And then what if the mid value is greater than the target value? In that case, you will shift to the left position. Okay. So that's what we have doing here. And then every time you do that, you run the loop again, you find a new mid value. And that's what we have done multiple times, right? We found the mid value 3 times. In the same way you're going to do here. And then at the end, you will get a value. If it is not if it is not there, you will simply return -1 as we have done before. So basically by doing this, what we are doing is we have seen 2 algorithms, right? Now we have to find the time complexity. Now what exactly time complexity is? It's not about number of seconds it takes to run your code. It's all about this. So time complexity simply means the measure of how the running time of an algorithm increases with the size of input data. So basically, let's say when you are testing a particular algorithm, you're testing for let's say 10 values or 20 values. But what if the values goes up? What if you have 1000 values? How will it will affect your time? Will it increase the time in linear section? Let's say if it takes 5 seconds for 10 values, will it take 10 seconds for 20 values? Or will it take more? Or will it take less? Okay. Or let's say you have 1 million records. Will it take 1 million seconds? That's the question we have to answer. Okay. Now, how will you do that? And that's where we have something called big O notation. Now, what happens in big O notation is we use this particular concept to understand your time complexity of your algorithm. If someone says, hey, your algorithm is not fast enough, you have to first find the big O notation of it. So why big O is because it is represented with the help of O, the big O. In bracket, you mention the order of n or something. So basically, it is also called order of or big O notation. Anything will do. So how do you represent that? You represent that with something like this. So we have O of, and then the value which is 1 will keep changing. So there are multiple things here. You can say we have O, big O of log n. We got big O of n. We got big O of n log n. We say big O of n squared, which is quadratic time. We got 2 raised to n. We got n factorial. Okay, so we got all this notation. But how do you find this? Okay, now this is tricky. So of course, in this particular video, you will not understand everything, but let's start with the basic. Now let's talk about the linear search. Now, if you go back to linear search, what we were doing there. Now in linear search, when you have 5 values, you take 5 steps. When you have 10 values, you take 10 steps. When you have 100 values, you take 100 steps, right? But let's say that is for searching, right? What about reading? If you want to read a particular element from the linear search or from the array, it's very easy, right? You specify the index value. Let's say the index value is 0, 1, 2, 3, 4. And then you specify, hey, I want the value at index 2. So let's say you say nums, which is the name of the array. And when you say 2, basically what you get is 9. It's very fast. So it doesn't matter what is the size of your array. It can be 1 million records. The time taken to get a particular element with the help of index value is constant, right? Because computer knows where that memory is. So in that case, I can say the big O, the time complexity for this is 1 because it is constant. Okay. Now see, it's not about one step. If you're thinking just because I've mentioned that it is only one step, it can be 3 steps as well. So let's say if you are reading a particular element and maybe behind the scene it takes 3 steps, it doesn't matter. It's constant, right? It can be 1 step, 3 steps, 10 steps. It should be constant. If it is constant, you can say O of 1. But what if you are searching an element? So if you have an array size of, let's say 10, it takes 10 steps. Now you'll be saying, hey, what if your element is at the start itself? Of course, it will take 1 step. But we have to go for the worst case scenario here. The worst case is, what if the element is at the end? What if the element is not even there? It will take 10 steps. And that's why we can say the order, the big O notation here will be n. What is n here? The number of elements in the array. As it increases, the time also increases, the time complexity. I'm not talking about the actual seconds, okay? So that's your linear search. Now coming back to the binary search, what could be the big O notation for binary search? See, the thing is, as the number increases, it will not directly increase the number of steps. Reason for that is, let's say we have 7 values. How many steps it takes? Let's say 3 steps, because we have to find the mid value 3 times, right? What if the size increases to double? So let's say from 7, we got 14. So what do you think? How many steps will increase? What if I say only 1? Reason being, even if you have, let's say 14 values here, let's say we have so many values, at the start itself, it will be half, right? You will get 7 values after 1 step. And then you basically increase 1 more step to find the mid. So that means when your value increases, it will also increase the number of steps taken, but not exactly n. Because in the linear search, if your number of values increases by 10, it will increase 10 steps. Here, as the number of value increases, it will not increase the steps in the same sequence. So what we can say is, it is something between constant. It's not exactly constant, but it is between the O of 1 and O of n. So it is between these two. And what comes between these two is O of log n. Now what is log n basically? So log n basically means we have a base 2 here by default. Okay, so number of steps it takes. So what exactly this n here? So let's say we have 8 values here. So when you say log 2 of 8, it will give the value which is 3. Okay, now why it is 3 is because log of 8 is simply means it will take 2 multiply itself 3 times to get 8. Okay, so as the number increases, let's say now instead of 8 values, we got 16 values. It will give you 4 because it will take 2 to multiply itself 4 times to get 16, right? So it will give you 4. That means as your number of value increases from 8 to 16, it will only increase 1 step, right? And that's why the binary search is log n. So your linear search is O of n, and your binary search is O of log n. So which will take less time? The log of n. Okay, and you can see the graph here as well. So this is elements, the number of elements you have in the array, and this is the number of operation it takes. Okay, so number of steps. So if your algorithm is following the constant time, it means it's here. It doesn't matter how many values you increase, it will be constant time. Log n is similar to, it's almost same as constant, not exactly same as constant, but it will take less time. So you can see log n is mentioned here. It's there, the wave is there, you can't see it, it's there. So what if you go with big O of n? So as your value increases, your time also increases, right? But there can be some worse scenarios as well. There can be some other algorithms which you implement which might take n log of n, which is worse than O of n. There might be some algorithm which will take O of n squared, which is worse than the O n log n. So basically, if you want to build an algorithm, try to make sure that you are here. If you are here, you're good, okay? If you are here, it's okay. If you are here, try to make it better. If you are here, that's the worst scenario. That means you're building an application which is not scalable. The moment you have 5 users on your server says, I'm good. The moment you have 1,000 users, it will struggle. Okay, so make sure that whichever algorithm you write, you follow this. Of course, in the upcoming videos, we'll work on some more algorithms. We'll see which one matches there, but you got the idea, right? So the time complexity simply means this definition, the measure of how the runtime of the algorithm increases with the size of the input data. And to represent that, we use big O notation. So I hope you got some idea. In the upcoming videos, we'll focus more on different algorithms and also find the big O notation for that. Apart from this, we also have some other notations as well. We'll discuss those things in the upcoming videos.